Hey, this is Chad Houston, and this is going to be a quick little tutorial on how to do pH. Okay, so first of all, the question is, why should we even care? One of the reasons I think we should care is because one of the things that I have for you up here, I'll try and show this to you. Move this out of the way. Let's take a look here, going from like 14 down to 1. One of the most important things to realize with the idea of pH is that it's basically telling us the strength of the acid. 7 is considered neutral, 1 extremely strong acids, 14 extremely strong bases. And as acids and bases were being developed and discovered and the concepts were being worked on, what they found was there was a huge range of concentrations. And so they couldn't do it on just a typical scale, so they had to do it on a logarithmic scale. Now the reason I say this is that when you have a range of approximately, let's say, here's neutral, and then about 4 to 10. Okay, so these will be weak acids, still can come in contact with our bodies. These will be weak bases. These can come in contact with our bodies. Anything above or anything below 4 or 3, it's kind of hard on our systems. And again, anything above 11 or 12, we really need to be careful. The biggest misconception is this. Some people think, okay, so if I have a pH of 6 and I have a pH of 3, pH of 3 is half of 6, so it must be twice as concentrated if it's becoming more acidic. That's not correct. That's a big misconception. Because it's a log 10 scale, okay, here's what happens. If you have a pH of 6 and go to a pH of 5, the 5 is 10 times more concentrated. And then to go to 4, so from 6 all the way to 4, that would be 100 times more acidic. And then if you go from 6 to 3, that's 1,000 times more acidic. So a pH of 3, this is 1,000 times more acidic than a pH of 6. And so essentially you're adding a factor of 10 each time. You're not just, saying, you're not just adding 10, but you're putting on a factor of times 10. And that makes a huge difference. So that being the case, we need to figure out what it is we are going to do to be able to calculate pH. So let's get started on that. So to calculate pH, there's something I would strongly encourage you to stop whatever you're doing and make sure to write this down, because essentially this is the mathematical relationships. For all water, which this will be in water, the equilibrium constant of water is 1 times 10 to the 14th, negative 14th, which means if you have the concentration of H, you have the Kw, you can find the concentration of OH. These are all in molarities. So that's a done deal there. Now, how do we go to pH and pOH? Okay, so if you have the concentration of the OH, it's just negative log of that molarity goes to pOH. So that's going this way. Okay, same thing here. If you've got the molarity here, negative log times pH, negative log of the acid concentration and molarity is the pH. Now, if you want to go back, so if we're going this way, if you're given the pH and want to solve it the other way, 10 to the negative pH equals the molarity of the H plus. And again, same thing here, 10 to the negative pOH is the molarity of the hydroxide. Okay, and then finally, this part's really cool. This is pOH plus pH is 10 to the 14th. So let's do some problems real quick. And here are typical problems that you can get. So you get a concentration of an acid, right? And it's a strong acid, and so 100% dissociated. How do you solve this problem? This is the concentration right here. That's this part right here. You punch it into your calculator, negative log of this, and essentially there's the answer. So you just type in negative log of 0.0034, 3.47. This would be the pH. I would really encourage you now, at this point, to make sure to check this. See if you can do it on your own calculator. A lot of times what's going to happen is we'll actually have a pH meter. Okay, and in a pH meter, suppose the pH meter, you stick it in your fish tank, or you stick it in something, fruit juice or something, and it reads 4.22. Okay, so what's the hydrogen ion concentration? And it's basically saying, that means what's the molarity? Well, again, to go backwards now, you would say, essentially, to solve for this, you would say 10 to the negative pH, which is the 4.22. Punch that in, and here's what you get. You get the concentration, right? And the concentration, so I said 10 to the negative pH, right here, okay, equals the molarity. So and I hard to show it on this, but it should be 10 to the negative 4.22 power. And notice we get this concentration here. Does this make sense? Well, up here we said a 3.47 pH was a concentration of 0.00034. If we have a higher pH, it's less acidic and less concentrated, and sure enough, there it is. And it would be, because it goes from about 3 to 4, it would be off by a factor as well. Notice there's 3 zeros here. There's 4 zeros here. Yeah, so that is well within the range. Now, what else can you do with this? Hey, guess what? If I have the pH, I can now solve for I know pH plus pOH is 14. If I have pOH here, again, I can solve for the concentration of the hydroxide, and you can do the same thing with the one down here. If I know the molarity of the hydrogen ion, I can solve for hydroxide, for pOH, and it's endless. So that essentially is how we do pH problems. What I would really encourage you to do, go back if you have any questions. Make sure you check the flipped assignment. There's going to be problems on this. Thank you very much, and have a great day.